Okay, so for our example problem dealing with light as waves, let's consider radio. Because radio, as we talked about, is part of the electromagnetic spectrum, so this is part of the light spectrum. So radio waves are, in fact, light waves. So we can do a radio example. So for our radio example, let's consider radio tower. Um, and let's look at KRLD. Okay, so KRLD broadcasts in the AM band, and KRLD has a frequency of 1080 kilohertz, and it broadcasts with a power of 50 kilowatts. Okay, so this is going to be the frequency and the power. And so what we want to know is for a person over here, a distance of 35 kilometers away, who has a little portable radio, then what is the voltage induced in the antenna? Okay, so we're going to say this is not just a generic portable radio. So this is it could be just plain portable radio with an antenna. Okay, so we're going to say it's an extra long antenna. So let's say the length of the antenna is 2 meters. Okay, so I want to know what's the voltage induced in that antenna, because the electronics are going to pick up that voltage right there, and then that's going to get you your radio signal. So to do that, we need to know the strength of the electric field at that point. Because we know that in the antenna, the electric field, the voltage is going to be electric field times the length of the antenna. We know that from our studies of electric potential. Okay, so now we're tying this back to what we've talked about earlier in the semester. So first of all, let's look at KRLD. So the frequency, 1080 kilohertz. So the wavelength, we know that C equals lambda f, so the wavelength is going to be equal to C divided by f, so by 3 times 10 to the 8th meters per second divided by 1080 times 10 to the 3 hertz. That cancels this, okay. And so what we find is that this is a wavelength of 278 meters. Okay, which is relatively long for wavelength for compared to some other things. But let's consider that, for example, this KRLD is an AM station. Let's compare this to like KERA, FM. So this is a radio station that's FM. So this is the NPR local NPR station. It has a frequency of 90.1 megahertz. So the wavelength here is going to be 3 times 10 to the 8th meters per second divided by 90.1 times 10 to the 6 hertz. And so that's going to be about 3.33 meters. And so this is fairly typical. Your typical AM radio station has a wavelength of hundreds of meters, and your typical FM station has a wavelength of about 3 meters. And so this it turns out to be very, very important in terms of picking up the signal and what you do with it. But we're gonna look here at like KRLD. Okay, how radio stations work is going to be another class. So here we have the antenna right here, and here we are a distance over here of 35 kilometers away. So if we assume that the antenna broadcasts omnidirectionally, that means that the signal is spread out on the surface of a sphere of radius 35 kilometers. Well, we know that intensity from physics 1, intensity is power over area. So this would be equal to power divided by 4 pi r squared. So that would be the 50 kilowatts, so 50 times 10 to the 3 watts divided by 4 pi times 35 times 10 to the 3 meters squared. And so what we find is that the intensity is going to be 3.25 times 10 to the minus 6 watts per square meter. So that's the intensity. The intensity is the magnitude of the Poynting vector. So we know if we've got an antenna here that we've got a voltage here. Now the voltage is going to go back and forth, back and forth, back and forth, because that's the nature of harmonic waves. It goes one way, then the other way. And so what we're interested in to find the maximum voltage, then the maximum voltage the other way. So the maximum voltage here is the intensity is related to the maximum. So we said that's E naught divided by 2 mu naught C, or E naught squared divided by 2 mu naught C. So that means that E naught is going to be the square root of 2 mu naught C times the intensity. So that's going to be the square root of 2, 4 pi times 10 to the minus 7 Tesla meter per amp times 3 times 10 to the 8th meters per second times the value that we had just calculated a little while ago, which was 3.25 times 10 to the minus 6. So 3.25 times 10 to the minus 6 watts per square meter. So that would give us an E naught that is 0.035 volts per meter. If we say that the length of our antenna, L, is equal to 2 meters, then that means V equals EL, E naught L, so this would be V naught, that's the maximum voltage. Remember the voltage is also going to be sinusoidal, V naught sine omega t. And so that's going to also be sinusoidal. So V naught will, in this case, end up being, well, 2 times 0.035 volt per meter, 2 meters. So that means V naught is going to be 70 millivolts. Okay, so that's the voltage. Now, you know from lab, 70 millivolts is actually a measurable voltage. And so if you have something that doesn't have much resistance, that can create enough current to do things. In fact, that it turns out to be the very simplest possible radio that you can make. So your simplest radio is basically an antenna, a long wire that then feeds into an inductor. So it feeds into an inductor and a capacitor. So now we have this tank circuit right here. Okay, and then we can ground one end of it right here. And so in your tank circuit, you would want to have some way of actually getting the signal out. So what you would normally do is you'd put into your tank circuit something extra in here. You would put a diode to make it one way, okay, and then you would have, or actually what you would do is you would have your tank circuit here, and you'd put like a diode, and then you would have speaker, and that speaker could actually be something like earbud or something. And so put it in your ear, and then that would actually be a radio. That would work as a radio right there. And so it's your simplest possible radio. You don't have a power source, you just drive the voltage here. It resonates here at a particular frequency. When it's resonating at that frequency, you have the maximum voltage across here. That maximum voltage then means that when it's resonating, then you get current flowing through here, and you can hear. So that would be your simplest possible radio, and what we call a crystal radio set. So that's an example right here of utilizing all the stuff we were just talking